All right, hello everyone. Um, I hope everyone's doing well. I am going to. This is our last review before the AP exam, um, and so the AP exam is Wednesday, the 5th of May, and so I will be having sort of an extended um, office hours, maybe Monday or Tuesday or something like that, where you guys can come and ask me any questions that you have if you're taking the AP exam. All right. So um, today I'm going to be reviewing simple harmonic motion. Um, and well, the most important thing that we want to measure in simple harmonic motion is the period, T, which is the time to complete not just a across, but a back and forth. Back and forth. Okay? So T is the period. Time to go back and forth. All right, so that is something that sometimes students think that it's just one way, but it's both. So we're talking about experimental physics, okay? So there are two sort of classic experiments that you can do um, with simple harmonic motion. And the first one is a simple pendulum. All right, so the simple pendulum um, is something where you have a ceiling and you have a pendulum bob, which has a mass m, and you have a string with a length L. What are you doing, Mr. Bugs? What are you doing? Um, okay, and so it's going back and forth. Um, and so the theoretical period for a simple pendulum is given by the equation 2 pi square root of L over G. All right? And so one of the things I want to point out is that this does not depend on amplitude. So amplitude being the size of the swing. And it also does not depend on the amount of mass that you have hanging at the end. Okay, so that is important to remember. So one of the experiments we could do, and actually if you are a cohort D student, you will be doing this experiment, is we could have different um, lengths of string and measure the period in this case. Okay, so you have length versus period. Okay, so you have a really long string and you sort of just like let it down and you let it swing back and forth, and then you let it down a little more and you just let it swing back and forth. So period versus length. Okay. Um, so this is not going to be a linear relationship because I have period on this side, but I don't have L to the first power on this side. So it's not a linear relationship. I have square root of L. Okay. Square root of L. And so what I want to do is I want to transform my data table, okay? Because I have square root of L in the theoretical equation, I would graph square root of L versus period, okay? So that is what is going to give me a linear relationship. So if I rewrite my equation here, I have period equals 2 pi over square root of g times square root of L. So I separated this into this single square root into two square roots, okay? And so if you were to do a graph of period versus square root of L, well, period is on the vertical axis, so period is like y. Square root of L is on the horizontal axis, so that's like x. And then the thing that multiplies x is the slope. So we can see that this is the slope. So it's going to be a straight line, and the slope of that straight line is 2 pi over square root of g. Okay? So the slope is related to the acceleration due to gravity. All right? So let me give you some variations on this experiment. Okay? You could do period versus mass of the pendulum bob. Okay? But remember, the period does not depend on mass. So, like, for example, if you found that the period was 2 seconds, then it's going to be 2 seconds for every different mass. But the idea behind this experiment is that you could prove period does not depend on mass. Okay, so you prove it. Another experiment you could do is you could do period versus amplitude. And in the case of a simple pendulum, amplitude would be the angle that it makes with the vertical. Okay, so you started out with different angles and you see how that affects the period. Again, the period does not depend on amplitude. So what you will find is that if the period starts out at 2 seconds, it will stay at 2 seconds. But there was a caveat when we said this. The period only doesn't depend on amplitude if the amplitude is small. So you'll have small amplitudes and the period is constant. And then once you get to big amplitudes, the period is going to slowly start to grow. Okay. So you could sort of prove that the period does not depend on amplitude only when the amplitude is small. Okay, so that's a variation of, just various things you can prove. All right. So the other simple harmonic motion system was a mass spring system. And this system, the classic experiment that you can do is you have a ceiling and you have like a rubber band, and I'm representing the rubber band as a spring. Okay, it has a stiffness K, and you hang a mass from the spring, and you pull the mass down and you let it go, and so it will oscillate up and down, and you record the period versus the mass of the okay, the mass of the at the end of the spring. So theoretically, the equation for the period for a mass spring system is 2 pi square root of m over k. All right. Again, theoretically, does not depend on amplitude. Okay, meaning that if you pull the mass down a whole lot and let it go, it's the same period as if you pull it down a little bit and let it go. And also we can see that there is no gravity in this equation, so it doesn't depend on gravity. So you could take this system to the moon, it would have the same period. You could take it to Jupiter, it would have the same period. Take it to Earth, has the same period. Okay? So anyways, just like the previous example, we have that the period is not related to mass, but square root of mass. Okay? So we need to transform our data table not to mass versus period, but to square root of mass versus period. Okay? And that's going to give us a linear relationship. So if I, again, rewrite the period of equation, it's period equals 2 pi over square root of k times square root of m. So if we were to graph period on the vertical axis and square root of m on the horizontal axis, that would be a straight line, and the slope is 2 pi over square root of k. All right? So if you found something that wasn't a straight line, then that would mean that your experiment does not support the theory of the mass spring system. Okay? So there are a couple of variations that we could do on this experiment. Hang on a second. So one variation would be to do, you could do period versus amplitude again. And you would find pretty much the same thing, that the period does not depend on amplitude, but that's only when the amplitude is small. Okay? So could do that. You could change up the springs. Could do different stiffnesses if you wanted to. So there are just some different ideas for experiments. Okay. So yeah. So I want to talk a little bit more about the theory of the mass spring system. So in particular, energy is conserved. Okay. So I'm going to switch to a horizontal mass spring system. So okay. So the energy is going to be the elastic potential energy plus the kinetic energy. All right. And we can evaluate the energy at any point in the motion of this object as we want to. So if we evaluate it at an extreme point where it's furthest away from equilibrium, then it has no speed and its position is equal to the amplitude. Amplitude is the maximum distance away from equilibrium. So we could write the energy also as 1/2 Ka squared. Or we could evaluate the energy at the moment where it is passing through equilibrium. And when it's passing through equilibrium, x is equal to 0. Okay? And so at that moment, it is reaching its maximum speed. So it doesn't arrive at equilibrium with no speed. It swings through equilibrium with its maximum speed. So evaluating the energy at that point gives 1/2 mv max squared. So you're going to get the same energy no matter which of these you use. This is just evaluating the energy at 3 different points. Okay? We can play around. We can set these two forms of the equation equal to each other, and we can get the position at a certain, or the velocity, I should say speed, at a certain position. And what you get is square root of k over m times square root of a squared minus x squared. So that is a useful equation. What this says, so we already talked about that the mass reaches its maximum speed as it is swinging through equilibrium. Okay? So that's where x equals 0. So if I plug in x equals 0, you can see I get square root of k over m times square root of a squared. And I get that the maximum speed is square root of k over m times a. So that's a useful equation. I forgot to talk about the defining equation of simple harmonic motion. The defining equation of simple harmonic motion is that the acceleration is minus a constant, which is called omega squared, times x, where x is the distance from equilibrium. Okay? And omega squared is a constant that depends on the system. So whenever this is your equation, you are going to have a position time graph that looks like this. Okay, it's going to have a certain amplitude. The amplitude just depends on how much energy the system is given, and the period is the distance between peaks. So if we applied this to the mass spring system, we would have net force equals ma, and then the force is the elastic force, which is minus kx, so minus kx equals ma, and then I have k over m times negative k over m times x equals a. So this is the form of the simple harmonic motion equation with omega squared equals k over m. All right. Now, omega is related to the period, and this is something that I would prove in AP Physics C. But it's related to the period through omega is 2 pi over the period. Okay? We can use this equation as well to figure out the maximum acceleration. So we can see that the acceleration gets bigger as you get further from equilibrium. So the maximum acceleration is going to be omega squared times the amplitude. Omega squared is k over m, so I get k over m times the amplitude. So these are all just useful equations, all right? Really what you want to think about is what is the origin of each of these equations, okay? So let me talk about motion graphs a little bit. So just to remind you, the velocity is going to come as a the slope of the position graph. So what I recommend doing is finding the spots where the velocity is 0. So that would be this point, this point. Finding the spots where the velocity is positive. Here it's negative. Here it's positive. And then just connecting the dots with a smooth line. Okay? And then if you want the acceleration, you just do the same thing again. Acceleration is the slope of the velocity graph. So I have acceleration 0, acceleration 0, acceleration 0, slope negative, slope positive. Boom. And then the maximum values are determined by the A max and the V max equations. So this is going to wiggle between plus square root of k over m times A and minus square root of k over m times A. The position obviously is going to wiggle between plus A and minus A. And the acceleration is going to wiggle between plus k over m times A and minus k over m times A. One thing I forgot to reiterate was that capital A is different from lowercase a. Capital A is amplitude, lowercase a is acceleration. They have different units. Physics is case sensitive, meaning uppercase and lowercase could have different meanings. Okay. Some other graphs we could make are the potential energy as a function of time. So the potential energy is 1/2 kx squared. So we're essentially squaring this graph, which turns all the negatives into positives. So we get something that looks like this. So it's going to have twice as many bumps because the negative, the valley, got flipped upside down and became a bump when you squared it. So you have twice as many bumps. Okay? So that is important to know. If I wanted the velocity time graph, the kinetic energy time graph, I would square the velocity because kinetic energy is 1/2 mv squared. So that would give me something that looks like this. Okay, notice how when the potential energy is high, the kinetic energy is low. And when the kinetic energy is high, the potential energy is low. Okay, so actually if we were to add these two together to get the total energy versus time, it is just a constant. Okay, in the presence of friction, so this is for a frictionless mass spring system. If we had friction, then all of these graphs would not be constant, but they would actually decrease in size as time goes on. So this would look like this. Each successive bump would be smaller here, and so on. Okay? So, if you're taking the AP exam, it might say something like, there is no friction, or there is friction, or how would things change if we added in friction? So you should know how to respond to that. Okay, so I hope this was helpful to review simple harmonic motion, and I will see you guys in class. Okay.